Hi everyone, welcome back. I hope you have had a great holidays. Unfortunately, I'm still at camp, so I'll be back on Thursday. But what this means is that for a lesson or two, you'll have to deal with me uh, teaching you through a video, which I hope is beneficial. So today, the plan is to actually take a few steps back and remember what a limit is. So this is where we ended off last term, but to refresh your memory, a limit describes how a function behaves near a specific point instead of at that point. Now, on your booklet there, I've given you a graph. This is a straight line with an equation of f of x equals to x plus 2. And now hopefully this is very familiar to you. And, well, if I were to ask you, what is f of 3? Well, that's just the y value when x is equal to 3. And the y value when x is equal to 3, clearly, if we look at the graph, is simply 5. And we can get the value of 5 just by subbing in 3 for x into the function. That's how the function behaves at x equals to 3. But that's not what a limit is. A limit, remember, describes how a function behaves near that point, not at that point. And so that's why I've written down there, below your graph, the limit of f of x, which is this straight line that you see here, when x approaches 3 is the y value that the graph approaches as we get closer and closer to x equals to 3. Now what that means is as x gets closer and closer to 3, what y value do I approach? Now clearly we can see there that we approach the y value of 5, right? Which just so happens to be the value of the function at x equals to 3 too. But that's not always the case. I think last term I mentioned that sometimes the function might not be defined at where the limit is given, right? So here's an example. So the second graph there on your page is the exact same graph, except there is an open circle at x equals to 3. What this means is that the graph is undefined at x equals to 3. It's just, there's nothing there at x equals to 3. Well, let's ask the same question again. When we approach x equals to 3, what y value do I approach? Well, clearly we can see here that the y value that we approach is still the same y value. It's still the same y value of 5. We still approach 5. And that's the key idea that hopefully we sort of understood from last term, is that the limit of a function tells us how a function behaves, or in other words, what y value we approach when we get closer and closer to the specified x value. Okay? Now, hopefully that's just a refresher. Now, I sort of brushed over this second idea, but this second idea is also equally important. And it's the idea that the limit of a function needs to be the same from both sides. And this is what we call a two-side limit, right? Now here I've drawn you a function, h of x. I haven't given you an equation, just take it for what you will. And if you look at that graph for a while, you can see there that there is clearly a break in this graph. Okay, there is this funky business going on here where you've got a closed circle here and then you've got an open circle here. Now what this means is that the limit, if you look ahead a bit, it's going to be different when we approach x equals to 3 from either side. So let's see what happens, right? When we approach x equals to 3 from the left, right? So here's x equals to 3, right? On the left, when we get closer and closer to x equals to 3 from the left, what y value do we get close to? We get close to a y value of 3. So my function approaches 3. But if you look up here, when I get closer and closer to x equals to 3 from the right, I don't approach the same y value. I approach the y value of is it 5? No, 6. I approach the y value of 6. Now, clearly, we approach different y values here. The limit is different from both sides. Now, when this happens, we say that the limit does not exist. It needs to be consistent. Both sides of the limit must agree, right? And since in this case it doesn't agree, the limit doesn't exist, okay? And so it's very important that we understand this conceptually before we begin to do the algebra. And I think last time we did a bit of the simplifying limits, which I hope algebraically actually makes a bit more sense after this explanation, right? So in case you've forgotten, here is the notation when you're trying to say the limit of f of x as x approaches 3. This is what it looks like, right? When you see big LIM, that just means limit, and underneath we write as x approaches to 3, right? So this big LIM means the limit of, what are we taking the limit of? Well, whatever function that goes here. And the thing underneath the limit, it means as x approaches 3. Okay, and so hopefully you remember what this notation looks like. Now, let's actually do some math. What do we do with all this? What questions will we be asked? Hopefully from last term you remember that the first thing that we'll ever be asked to do is to actually evaluate a limit. Now, we're just going to assume that the limit exists, okay? So we assume that it exists for now, because I'm never going to ask you a question where the limit doesn't exist, right? What do we do then to simplify a limit? Well, really, we want to just substitute the limit in. That's the end goal. But sometimes we can't do that immediately. And here, if you look at this first example here, evaluate the limit as x approaches -1 of the function x squared plus 2x plus 1, we can simply just substitute the limit in to the function itself. So here we've got x equals to -1. We're just going to sub -1 in, right? So this simply just becomes -1 squared plus 2 times -1 plus 1. And if you evaluate that, you'll just get 1 minus 2 plus 1. So you will get minus 2. And that's really it. We just substitute the limit in. Now, of course, it's not as simple as this all the time. Sometimes, if you look at example 2, you actually can't substitute the limit immediately. The reason why is because most of the time you have a fraction, and on the denominator, if you substitute a specific number in, it might not work. You'll be dividing by 0. Actually, in the case of example 2, you actually can substitute -2 immediately. But for the sake of this example, the idea is we want to simplify the limit as much as possible before we substitute the limit in. So in this case, we actually can simplify it a little bit. If I factorize an x out of the numerator, I'll get x bracket x minus 3, and on the bottom I'll get x. And then if I factorize x out of the top, you can see that we can just cancel. So we'll just cancel these. And what I'm left with is the limit as x approaches -2 of x minus 3. And of course, we just sub in -2 because we can. And that just gives us -5. Okay? All right, so example 3 and example 4 are examples where you actually must factorize and you must cancel out factors because you actually can't substitute the limit in immediately. So here we are, we've got x squared minus 5x plus 6. And hopefully you remember how to factorize this. And when you factorize this, it is simply a monic quadratic. So we think of two numbers that multiply to give you positive 6 and add to give you negative 5. And after you think about it for a while, hopefully you land on negative 2 and negative 3. And of course, now you can see that I've got two factors that are the same, right? X minus 3, x minus 3. So we can cancel those two factors. We can only do so because they are multiplied. And now I can substitute my limit in, because I only have x minus 2 now. Whereas before, I had x minus 3 on the bottom. And if I substitute 3 in immediately, I'll just get 3 minus 3 on the bottom, and I'll get 0. So I couldn't substitute my limit in immediately, but now I can. Okay, and so let's do that. So 3 minus 2 is simply just 1. Okay, and I'm not going to go through example 4. Hopefully you can do that. It's just difference of two squares. So I'll leave that exercise for you. Okay, now I do want to discuss some special limits. Now, this is something that I didn't go through last term because I thought it was a bit too complicated for the last week. So hopefully you're fresh and your mind is able to tackle this concept. So sometimes we have these special limits. Now, I'm going to start with this, and it might be a bit weird, but it'll make sense as we go along. So I want you to remember what the graph of y equals to 1 over x looks like. If you remember what it looks like, it's really just a hyperbola. And it looks something like this. That is the graph of y equals to 1 over x. Now it turns out that we actually have some special limits when it comes to the graph of 1 over x. Namely, is when x approaches infinity, so when x gets really, really big, I'll show you in blue, when x gets really, really big, what happens to the y value? Well, you'll notice that the y value approaches a really, really small number here as x gets really, really large. And so for the sake of this limit, what we say is that that really, really small number, it's pretty much 0 because it's so small. And so we say that the limit as x approaches infinity of 1 over x is 0. That's where our first special limit comes in. But what about what happens when x approaches 0 instead of infinity of the same graph? Well, that's where we need to apply that idea of the two-side limit. Remember how we said that a limit must be the same when we approach from both sides? If we approach from the right towards 0, what do we get? We get a really, really big positive number as a y value. Yeah, as x gets really, really close to 0 from the right, our graph climbs all the way up to a really high y value. But then what happens when x approaches 0 from the left? Well, it turns out our graph goes really, really steeply downwards, right? It goes to a really negative y value. Now, clearly, those aren't the same thing, and so the two-side limit doesn't exist there. And so that's why the limit does not exist, and that's why we have this second result. Now, what about the result on the right? Now, I'm actually going to sort of leave this as a bit of an exercise. I would like you to actually graph this function in maybe Desmos. And I want you to ask yourself the question, what happens when x gets really, really close to 0? And hopefully you can convince yourself that, in fact, this limit is actually also equal to infinity. Okay? But in case you're still confused, when I come back, I can explain. Okay, but I encourage you to actually think through this and maybe graph it on Desmos. Now, how do we use these special limits to help us evaluate limits? Well, here we are. We've got some limits here now. And it's important to remember that we always want to start by simplifying everything as much as possible first before we decide to use these special limits. Okay, so we want to apply what we've learned already and think about how we can simplify it. So hopefully you look at that and you go, oh, that's just the quadratic. Let's just try factorizing it, right? So if we look at our first question here, x squared minus 8x plus 12 over x squared plus 3x minus 10. Let's try factorize this. Now, when we factorize the top, we get x minus 6, x minus 2. When we factorize the bottom, we get x plus 5, and then x minus 2. And so we see here that, indeed, I actually can factorize. So let's, oh, sorry, not factorize. I can indeed cancel, is what I mean. So I can cancel these two factors here. And what I'm left with is the limit as x approaches 2 of x minus 6, x plus 5. And then I can just sub in my limit. Easy peasy, right? So this becomes 2 minus 6 on the top, 2 plus 5 on the bottom. So we get minus 4 over 7. That seems easy enough. We didn't have to use any of our special limits. And that's okay. So let's actually see what happens when we actually need to use one of these special limits, right? And hopefully you're looking at the questions B, C, and D, and you can see that instead of the limit as x approaches 0, it's the limit as x approaches infinity. That's where we need to use our special limits. Now here is, I'll let you know the trick in just a second. But basically, let's write the question down first. Here we are. We've got the exact same question almost, except now we are approaching infinity. So notice that the function itself in part B is exactly the same as the one in part A. So let me factorize it exactly the same way. We get x minus 6, x plus 5. Remember the x minus 2's will cancel. Now, how do I do this? Well, this is where we need to learn a trick. Now, the trick is we are going to divide each term by the highest power of x. Now, in this case, if we look at the function here, what is the highest power of x? It's just x to the power of 1, right? There are no x squareds here, or x cubed, or x to the power of 4. There's only x, and so that's the highest power. So let's divide every single term by x. Now, I'm allowed to do this because that won't change the question itself. It's like dividing everything by 2, right? And like everything, top and bottom. So I will get x over x minus 6 over x divided by x over x plus 5 over x. Now, x over x, that's just 1, right? Remember to continue writing your limit as we go along. That's just 1. 6 over x. Ooh, right, so that's where we need to be a bit careful now. When x approaches infinity, for 6 over x, what do we get? Right, so this is where we need to look up at a special limit again. And the one that we really care about is the first one, right? It tells us that when 1 over x approaches, when x approaches infinity, 1 over x approaches 0. And that should make sense. if I have 6 divided by infinity, if I have 6 divided by a really, really big number, like 6 divided by a billion, I'll get a really small number, which is pretty much 0. And so that's why this thing here, it becomes 0 when I substitute the limit in. And so in my next line, instead of writing the limit, I'm going to substitute infinity in. Now, obviously, infinity is not a number. It's a concept, right? But when I substitute infinity in, I will get 1 minus 0 over 1 minus 0, and that gives me 1. Okay? Now, I would like you to actually use this example here, and I'd like you to give C and D a try, following the sort of same principle that we are following here, where we divide each term by the highest power of x, and remembering that 6 over x, or 6 over x squared, or 6 over x cubed will always approach 0. Okay? Okay, so let's go through what continuity is. What is continuity? Well, a function is continuous if we can draw the function without lifting up our pen. What that means is a function is only continuous if there are no breaks in the graphs. Right? There's like no jump, right? Like if I can't lift my pencil while drawing the graph, it must be, all connected. And if you can think of a continuous function as a graph that's always connected to every single portion of the other graph, right? So there's no like separate graphs. It's just one straight or curvy or connected line. That is essentially what a continuous function is in plain English. But of course, we want to be a bit more specific. So a function is continuous if and only if the y value at any point is equal to the limit at that point. Sorry, that should be an x. Now, let me, of course, give you an example of what a continuous function is. Here we are. Here's a parabola. You can see that you can draw that parabola without lifting up your pencil. You can just go, right? And, of course, that means it's continuous. Whereas your hyperbola, on the other hand, the one on your right, that is, unfortunately, not continuous because you can't draw that without lifting up your pencil. You must lift your pencil physically and draw the other branch, right? And that's because there is an asymptote there. There's a vertical asymptote at x equals to 0, which means that the graph is undefined at that point, which is what I mean when I say there's a break in the graph, right? It's like the graph decided to take a break. That's what I mean, right? There's a break in the graph. And graphs that have breaks or asymptotes, vertical ones I mean, they must be discontinuous. They're not continuous for the entire domain, right? Now, I say this just to sort of make sure you understand the difference between continuous and discontinuous functions. But of course, for the rest of this topic, we're mainly going to be looking at continuous functions. But it's good to be able to distinguish between the two. And that's a skill that I think we're just going to briefly touch upon, right? So let's have a look at these questions here. It says, determine whether the following functions are continuous at this x value here. So I just gave you the definition of what a continuous function is. It's right up here, right? It says that the y value at that specific x value, in this case it's 1, f of 1 must be equal to the limit of the function as x approaches 1. So let's actually test that out, right? So what is f of 1 for part A? Wait a second, we have a problem, right? We can't actually sub in x equals to 1 because we'll get 1 minus 1 on the bottom and that'll just be undefined. And so that means that the first function that we see there, it can't be continuous. It's not continuous because there is no y value when I sub in x equals to 1. It's undefined, which means there is a break in the graph. There is no way this function can be continuous if there's a break, right? Now let's try part B. Part B says we've got a function, and if you look at that notation there, that is a piecewise function. This means that the function is equal to -3 only when x is 1, but then it's equal to this other stuff that you see there when x isn't 1. So let's try f of 1. Well, f of 1, the function already tells us is -3. But what is the limit as x approaches 1? Well, let's see. What can we do here? Well, if you look at that, that just sort of looks like the limits that we've been evaluating thus far. And you know that when you see quadratics, your knee-jerk reaction should be to factorize, right? And so when you factorize that, you'll get this. And immediately we can see that we can factorize and then cancel x minus 1. And when we do so, we get the limit as x approaches 1 of x minus 4. And when I sub that limit in, what's 1 minus 4? It's equal to -3. But wait a minute, that's also f of 1. So what that means is this satisfies my definition of what a continuous function is. Therefore, yes, it is continuous. Now, you're probably thinking, so can't I just like graph this in Desmos, and then if I see that it's like a smooth curve, it's continuous? Well, yes, that's the idea, right? Either you can do the algebra, or you can just graph the graph itself and just go, well, look, I graphed it. There's no breaks in the graph. It's got to be continuous, right? Well, yeah, you can do that too. Okay, so really, this algebraic definition is simply a roundabout way of showing something is continuous without actually drawing the graph itself. Okay, so I would like you to give part C and part D a try using sort of the same idea of looking at the y value and then looking at the limit as x approaches that x value. Okay?